Okay, so welcome back. Now we are going to have a couple of lessons about Bayesian statistics. The intention is to go with the basics, so we are doing the first hour. The first part of the lesson is going to be mostly theoretical, just to introduce the concepts of Bayesian statistics, and the second part it will be a little bit more practical, so we are going to see how to use it and how we can run some analysis. The initial intention was to doing it in R, but then we switched. I talked with Mark a bit about this. We thought that also introducing JASP, which is a nice software to run this analysis, which is based on R, on bias factor package, it could be probably more easy to become independent more faster, let's say. And so it could be a good idea to propose you how to run this analysis in JASP, considering that it's easy to extend then in R, and I will give you also some advices to extend this analysis in R. So that's the main plan for the next 3 hours, a little less probably. So who is speaking? I'm Daniele Romano. These are my contacts if you need any additional question, if you have any additional question at the end of this week. I didn't send you the link with the slides, because in my personal little experience it's better when it's more theoretical than with the earlier lesson with Giulio. To have the slides later after the lesson, so you pay attention to what's on the screen and what I'm saying, and not on your screen more. That's the idea, but I don't know. Let me know if it doesn't work. But you will have the slides. Okay, so who am I? Well, my background is mostly in Bicocca. Now I have to say that I'm supposed to be half in Bicocca and half in the University of Salento, because I won a grant there, but I'm mostly in Bicocca, I have to say. And I studied on all these beautiful places. I've been lucky enough to stay there a few times. And I'm a psychologist, and my background is actually in experimental psychology and neuropsychology, and I switched to psychometric at a later stage of my early career. But now I have to say that I'm much more and more on that side, and I like it a lot, I have to say. But my background is in neuropsychology especially, so I came from this tradition where we have very small samples with a lot of problems with the statistical analysis. So that's why I switched, basically. And I'm speaking about Bayesian statistics because I'm a bit I won't say expert. I know something about that, and I'm part of this summer school that I organize with Michele Scandola, who is a very good researcher from University of Verona. This is not a real advertisement, because we didn't plan yet to organize the 3rd edition, but hopefully we will in 2 years. So if you are interested in deepening the Bayesian statistics, you can look at this website. That will be updated as soon as we know that most of the lectures are confirmed for the 3rd edition. Probably it's not this in 2022, probably it's going to be in 2 years, because it's more feasible to do every 2 years instead of every year. So if you will be interested in deepening this, just keep in touch. And another little disclaimer that I want to point out in advance is that things can be quite easy from a certain point of view, also in the Bayesian world, but it's also easy to be extremely complicated and without clear solution. And I have to say there are a lot of different levels of experience with this kind of analysis. I'm more in between. I think I'm a user-friendly, not a real expert. I'm in between of user-friendly and expert. Probably I stand in the orange part. And I don't know how many of you can be at the same level right now. We will try a little assessment. If you are user-friendly, probably this next hour will be a little boring for you, so we can see later. If you are user or naive, maybe it's useful. And Marco, maybe you recognize this distinction of levels. What can you do with Bayesian statistics? Well, I have to say that it's an entire world. It's not just a way to do inferences, although this is an important part and we will focus on that. But you can do a lot of things. For example, you can design efficient experiments, and we will see a little bit how. You can run inferential statistics, so having indices to take your own decisions on what hypothesis is better or works best, and we will deepen a lot, not a lot, we will go much more on this, but you can also use Bayesian statistics in neuroimaging, for example. Now there are more and more groups that use this kind of analysis. The most famous probably is dynamical causal modeling, which is an advanced method to do fMRI. You can do machine learning, of course, and recently it has been used also to contextualize new theoretical models. For example, the Bayesian brain is a very influential model to intend the brain in the recent years. And everything starts from this little nice equation, of course, with their own specificity. So we will focus on this. So we can have, with Bayesian statistics, we can have a sort of version of the null hypothesis test. We can also have something very different, but the final goal is not that different. The final goal is to have the evidence to say something with more certainty than before. So you must do it? No. It's always necessary to run Bayesian statistics? I don't think so, personally. There are people that think it must be run always and just analysis with Bayesian stuff. I personally don't believe so. I think it's potentially useful, and if you embrace the philosophy that stands behind, maybe can give answer to different questions, can be used to answer different questions also. So it's potentially useful, it's not mandatory. I said that you can, now it's more and more frequent that you find out this paper. Maybe you saw a few papers with these nice brains with little spots and connection between them. Usually behind this there are this dynamic causal modeling, which is a method to basically design models and to test which one fits better with your data, and you use Bayesian indices to decide which one is better. And another one that I never deep enough in this, but I think that I wish to put more attention on this, is to use Bayesian methods to design efficient efficient experiments. Why so? Because, for example, in psychophysics, you can have an experiment, classic experiment to define threshold and slopes of your whatever perceptions. You may have 300 trials, and with adaptive methods based on Bayesian selection of items, you can drop up to 60 trials to have the same accuracy in your threshold estimation. So it's a different way of using the adaptive methods and the update of the Bayesian statistics to have very efficient experimental design. So I'm not expert on this, I have to say. I wish to become more expert on this because I think it's very useful. Okay, before going Bayesian, if you have an internet connection, I ask you to switch just for a second to this one. So you go to www.menti.com, you enter this code that you see up here, I can tell you, and just answer to this couple of easy questions. It's the code is 58830613. You can do it also from the mobile if it's easier. Let's see if it works. Okay. Okay. We have 13 answers, 14 answers. Okay. Everyone, more or less. Good. So, you are not very naive, probably, if you answer in this way. So, how many of you already have experience with Bayesian statistics? No one? So you really put a lot of trust in my lesson. Thank you. Thank you so much for the confidence. But yeah, we will use this because this is your beliefs. Okay, let's try to start using the terms of Bayesian words in what you can do after this lesson. So now, by now, without any other information, just we saw each other at lunch and in the lesson before, for most of us, you think that after this lesson, it's likely that you can do something, okay? So keep in mind. And that's okay. Let's go back here. Okay, I think we need to say something before going real on the Bayesian side. Because one key point is why we need statistical indices. And it's also about Bayesian statistics. So we need it to take decisions. There are different schools. I know these are old statements, things change and advanced on this, but when we speak about this, we also have to consider either the exact statistics of how we can assess the evidence for something, how do we assess the evidence, but also how we should do that. And these are somehow connected one to each other. So we know that statistics sometimes becomes an unthinking ritual. We know that p-value below 0.05 is good, above 0.05 is bad. Yeah, somehow we've been exposed to this consideration, and if you are here, probably you are already over this simplistic view on statistics. But we know that in our classes there's this problem. So another point that I wish to express is, again, my belief that tests are tools somehow. They are combined with a philosophy behind, a philosophy of science also, I have to say. But it's a tool and you have to use it. And it's not the truth per se. Okay? And so, even if you don't believe in everything about the Bayesian world, then you may look at it as a tool, just for that. So, it can answer something else. So now we come to a more crucial point. The classical definition of probability is that probability of an event is the ratio between the number of favorable cases and the number of possible cases. Easy stuff. But we know that we cannot really do this with complex things. So we have the frequentist definition of probability, which is defined more as the probability of an event is defined as the relative frequency that it assumes on a large number of tests or performed under the same conditions. But this is an ideal situation. We know that we never have exactly the same condition, either in replication studies. So it's an ideal definition, and that's one of the more critics that have been exposed to the frequentist definition of probability. The subjectivist or Bayesian theory see probability as beliefs. So the confidence that you have that something will happen. And this introduces, from a certain point of view, the problems that we go to the subjective point. But if you keep in mind that's the definition of this viewpoint, then it's more clear what comes later. So we have to keep in mind this definition of probability to understand where we are moving with the Bayesian world. Maybe we cannot agree with this point, but if we see something interesting in this, then the methods works. Okay.
So is it correct to say that frequentists assume the kind of truth to be discovered?
Yes, I would say more. It's an objective. They pretend to. They pretend. I'm also frequent. So, but the idea is that there's an objective evidence, while in the Bayesian statistics, you are not interested in the objective evidence because you can never demonstrate that it's objective. So it's better to define the subjective that stands behind your decision and make it transparency over that subjective point of view. So that's the big difference in this perspective. But yeah, that's the key point. Okay. So there's always a nice quotation from Feynman that works when you have to prepare a presentation. That works here. Scientific knowledge is a body of statements of varying degrees of certainty, some most unsure, some nearly sure, none absolutely certain. So from this perspective, if we adopt this perspective, then again the subjective viewpoint on that works good. So how does it work? Now maybe you understood why I asked you how likely you believe that you can answer this. So we are putting our beliefs on that. When we approach a scientific question like this one, these are perfectly scientific questions. How strong is the evidence for anthropogenic global warming? Okay, that's a question that we can use our methods, whatever the method we want to use to answer this question, but also a question like, should we believe in subliminal priming given the literature on it? Again, now we are speaking about belief. Maybe we are not used in science to think about how much I believe. But when we speak it one to each other and we read some, let's say, paper that we don't really trust in their data, but they probably react perfectly, so it's not, but still we don't believe. So it's inside of our way of looking at also scientific questions, speaking about beliefs. Also speaking about the beliefs in the evidence that we have. So we put a question usually in the Bayesian way of reasoning, and it's not far away from any other, from the frequentism approach, I'd say. But then we instead of making prediction, you have to assess how much you believe in that possible answer. So you may say, okay, I think that it's the coin is fair in 180% of the case. So I put my trust on that. Then you run your experiment. So you acquire the data and you run the statistics, whatever the method that you have, and you develop a belief after having a sort of prior belief, your evidence, so your data. You develop a posterior belief. Okay, so you have a new belief that it has been updated after having seen some data and having some evidence. So these are the three magic words, I would say, in the Bayesian environment: prior beliefs, evidence, and posterior beliefs. So these are the three main concepts.
This means that Bayesian statistics is much more flexible, because in traditional you have P05 as a prior belief, let's say in those statistics anymore. But in this case you can have any kind of...
I'd say that Bayesian statistics is more flexible, but not because of that.
Okay.
Because of the threshold, you can reproduce the exact same problem within the Bayesian world, and we will see, because we will use it. The bias factor now is more and more used, and it's going to have the same problem of threshold. 3 is good, then if it's 2.9, you believe that it's not significant. So you are not fixing that part, although you are making more explicit that part. And I think this could be of help, because it's more declarative when you have to approach these thresholds. But it's not fixing the threshold problem per se. Okay, in general, not just in the Bayesian world, we can think about the inferential indices and inferential statistics as instruments to take the best decision, informed decision given the available information. Okay? Given if I'm acting as a rational thinker, I have some information and I have to take the best decision. That's the key point for all our analysis. So let's make an example. Oh, I didn't put the animation. Well, there's no animation, so I will do the animation. Let's pretend that I'm the president of this nation that is called not so well planned. So I have limited amount of money, and the COVID spread out. Unfortunately, we don't need a lot of imagination for this. So before running the vaccine research and having an answer, I have to decide where to bet my money, because I should invest on the mRNA vaccine or adenovirus vaccine, which nation, which brand, okay? And I have very few information. We know that adenovirus vaccines are more classic, so more probable they will achieve a good result, but how good? mRNA vaccine were already on the verge to emerge as a best solution before the COVID. Where one should put money. Without information, this is a very difficult task. So all our government had to deal with this, and it was very difficult. The EU probably bet on the wrong horse, I'd say now, initially. But the key point is that after you collect some evidence, so after a year of research, we have the evidence, and we should revise the budget. Now, you can do with all the methods that you want, but the Bayesian framework is in some way thought to do. It was not thought to, but it fits very well with this reasoning of updating the decision. So you collect new information, and you revise the decision, and you can do on a cyclic way. The point in this case is that when you have to do it, after each month, after each data collected, maybe it's not a very good idea. But you can say that after 6 months, after a year, you can decide to update your vision on this with all the new evidence and having new beliefs, and use these beliefs to take your new decision and revise your budget. So it's a practical issue. Okay, so this is I think the framework where we should think Bayesian statistics. So it's not an answer for everything. It's a different tool with a different perspective on probability, which may work in some situation. In my experience, works well, but in some other cases, you don't need to use it. Okay, so why we are going Bayesian now? Well, the development of the Bayes theorem comes earlier than the frequentist approach. So it's from 18th century, so it's earlier. So why we didn't use it and we go to null hypothesis statistical testing, and which achieved a lot of results with that. I mean, it works. Otherwise, we wouldn't have this kind of development in our field. It works very well. Well, it's not just because of this, but probably contributed in pushing towards a new methods, new vision on this. The crisis in reproducibility, at least in psychology, in my vision, well, and there are also people more influential than me, that showed that somehow pushed towards new definition of statistical, or of the threshold, for example, the p-value, of the use of power analysis. We will see much more. Marco will give a much better lesson on how we can fix the problems of the reproducibility crisis in the next days. So this gave a push, probably. It's not just that, and we'll see why. So we had a lack of confidence in the meaning of the p-value, also brought by this reproducibility crisis. But most importantly, probably, we have the development of computers, because we will see that some part of the calculation that goes behind the Bayesian statistics can be time-consuming and complicated. And so we need a lot of computing power. And to do so, we also have there have been developed also better algorithm to approximate the posterior. We will see why we need to approximate the posterior. And also these somehow have been influenced by a new theoretical framework. And I have to say that I didn't put here, but also the development of practical tools like JASP, for example, and we will see, pushed because it made it easier to access this new word. And I think it was an additional push toward the use of Bayesian statistics. So back to the future. Okay. What does it mean going Bayesian, let's say? So we saw that everything stems from one single equation, quite simple to see on the screen. And the core idea that stands behind is the idea of conditional probability. Okay, so I have basically how we can condition an hypothesis on data, and we see what is conditional probability. So it has been developed by Bayes, but Bayes gives the framework. Actually, the mathematical application was developed by Laplace and Price. That's why there's a very nice package that is called Laplace Daemon that for running Bayesian statistics, because the mathematical part was moved from those two. And again, the idea is the possibility of updating our beliefs. So these are different ways of saying more or less the same thing. So we can calculate the probability that an event occurs given the data while considering our previous knowledge. Okay, I have some knowledge, I collect new data, and I calculate the probability. Or I can say, given a set of information that bias my decision, so I have information that gives me a bias, how new data change this bias, okay? That's the core idea. How it works? Well, first we have to consider that the conditional probability is not the joint probability. Imagine this situation. Well, I like basketball. Maybe this doesn't work for everyone, but I have other examples. So imagine to see a scene like this. So I see this ball that enters, and I say, how likely that this shot was a three-pointer? Okay, I have some idea from the ball, the net, and they say, okay, I have some probability. But then I see this guy on the field. This is the best shooter ever in the basketball history, and now I start thinking, maybe this is a three-pointer if he is on the field. So how likely this is a three-pointer? Why this is not symmetrical? Because if I think that, what's the probability that this is a three-pointer, given that I know that this guy is shooting? Okay, it's quite high. But if I reverse the condition, what's the probability that Steph Curry is shooting, given that it's three-pointer? Well, it's much less, because there are a lot of players on the field. Okay, so it's not symmetric. And we can see maybe in a different example, and with plugging also the numbers. So we have this situation. You are at the cinema, you have this person in front, and you need to pass for some reason, and you know how to refer to this person as a sir or as a lady. Of course, you can say just excuse me, but let's keep this alternative solution. So the probability from this viewpoint is that we have in front of, without seeing anything, the probability is that it could be a male or a female, half and half. But the probability that has a long hair, given that it's a woman, it's 0.5. The probability that to have long hair, given that it's a man, it's 0.04. Okay. So when we apply this into the joint probability, we have this kind of situation. So these are the women's side, and we have a split of the two squares, while on the male side we have this kind of situation. So it's more unlikely. Okay. So we can plug all the numbers into the Bayes theorem, and we end up without knowing where we are. So when we have a prior probability of 0.5, so exactly the same probability that it was a male or a female, with this kind of chances. Okay, so it's more safe to say, excuse me, lady. Same situation, same cinema, same everything, but we are queuing in the restroom of men. So it's very unlikely that this is a woman, although it's still possible. So we put a very little probability on our prior expectation that this is a woman, but still the joint probability remains the same. So we have this kind of situation now. And if we plug in the number into the Bayes theorem now, we have this situation. So we have 80% chances that this is a man. So we say, excuse me, sir. Okay? So that's the core idea that stands behind all the Bayesian analysis, I have to say, which can be seen as simple, but can get complicated when you increase the parameters and all the stuffs, practical stuffs. And we can see in another example close to us. So let's imagine that exists a rare disease that affects 1 person every 1,000. And a person is a positive at the test, which is correct in 90% of cases. So it has a false positive rate of 1%. What's the real probability of having the disease in this kind of situation? Well, we have the Bayes theorem to solve this situation, so we can plug all the numbers. We can see much more in detail. So the probability of actually having the disease, given that the test is positive, okay, is composed by the probability that the test is positive, assuming that it's true that I have the disease, times the overall probability of having the disease prior any other information. So the probability that the disease exists in the population by the probability that the test is positive in general. And if we plug the number, it's still quite small, the chance that I have this kind of disease, still 9%. That's why when you go to the doctor and they say, it's better if you have a second test, okay? Because one test, it means, but it doesn't mean that much in the end. And we can see graphically what does it mean this. Sorry, yeah, I have already plugged in. If we do a second test, now our prior probability is sorry, it's later. Don't consider the last one. So we can put it graphically. That's 1,000 of dots. And this is our positive test, okay, with the disease. But that's the real distribution where we have to understand if I'm this guy or if I'm one of the green one. So that's where it comes from, the 9%. Okay, that's where it comes from. I hope this is more clear in this way. And now the idea of updating. So what's my posterior belief is 9%. If I run a new test, what I do is basically that 9% becomes my prior beliefs. Because now I have already the beliefs that I have 9% chances of being sick or that disease. And if I run again an independent test, of course it's independent, all the practical stuff to be reliable as an independent measure, and I replug the numbers and it's again positive, the test. Now I have 91% chances of having that, disease, okay? So what was my posterior becomes my prior. I collected new evidence, it's positive again. I update again my beliefs, and now my second, let's say, posterior beliefs is to be sick in 90% of the cases. This is okay, this works, that's what stands behind. How we can, how it could be useful in our situation, in our researches. Well, we can see this update consideration in this way. What's the plausibility of a theory A, of an hypothesis A, given the data, how we can determine? Well, what's the plausibility of the data given my hypothesis, by the plausibility of observing that data, that kind of data, under all the other hypotheses, times the plausibility of A in general, which is my prior beliefs. This is quite complicated, at least for me, but again, to get familiar with all the Bayesian lexicon, which is unfortunately sometimes just different, not for real good reasons, but sometimes it's for good reasons. We have these beliefs after, okay, after observing the data, which is called posterior, which is determined by my data, so the likelihood, the evidence that I have in the data, plus my prior beliefs. So plus what I believed before. Now, the problem with the calculation that I told you is with this P of y. Because P of y is the probability of observing the data under all the other, all the potential theta, all the potential hypotheses. And these can be very complicated to calculate, especially when you have 2, 3, 4,000 of parameters. It becomes untreatable. So it's unsolvable analytically, but we will see it has been developed a few methods to approximate the posterior beliefs, and from the posterior we can obtain the evidence, so the marginal likelihood. It is called the average likelihood or marginal likelihood. So with the easy numbers like the one that we had up to now, we can calculate it analytically, and having a perfect answer. Without it, we can approximate it. Let's see a quite easy, let's say, example of how it works with numbers. Classical situation, I have to flip a coin, and I have to decide if I trust the coin, so if it's a fair coin or not. And my prior belief is that, yeah, I trust it, but let's say I'm still uncertain. So what I do is to spread, let's say, around all the field of the possible parameters that it has, the coin in the flipping coin, with a peak at the fair point, so it's peaking at 0.5, but I'm not excluding all the other possibility of that coin to be flipped. So by doing so, I really want to trust on the data that it's coming, and I put just little information in the prior. Okay, we can deepen this part later. So that's my prior belief. My prior belief before running the experiment is maybe it's fair. Then I flip my coin 20 times, and I have 15 heads out of the 20 flips. And what I do is to update my distribution of the possible value that it assumes the parameter that stands behind the flipping of the coin after observing the data. And you see that it assumes this skewed distribution around close to the value of the ratio of 15 out of 20, and it's narrower if you look as compared to this one. So it means that I'm more confident now that it's between 0.6 and 0.8, let's say, after flipping the data. But this is not the proportion of 15 out of 20. It's integrated with this prior belief. So how it works exactly? Well, with the binomial and beta distribution, it's pretty easy to see, because these are the value of my prior. So I just put numbers of on the, let's say, to make it simple, this is number of head, this is number of tails, for example. So it's 2, 2, it's fair. So I expect that the odds is in between, it's 0.5. And I put little information because I put just few evidence inside this prior belief. And when you update this with the binomial, you simply sum your new observation to this value. So we will see with the numbers, but basically, if I have a 15 out of 20, this becomes 17 and 7. Okay. And you can see this is the exact calculation, but the point is that is what I told you. So it becomes a beta with 17.7 in the value of the parameters. Okay, so now I overlapped the prior. Okay, this is exactly the green line that you saw before, and you see that it's over. It's basically completely swamped by the data that I observed. Why is it so? Because I put very little information into the prior. So I didn't have a strong beliefs before running the experiment, and I put something that it should be around 0.5, but whatever is fine to me, and I trust only the data. So from this perspective, it's not very Bayesian, let's say, because I put very little information in the priors. It's more or less useless, the prior. Still, the prior defines the fields where things can happen. Okay, nothing can. We will see later, but the prior defines where you can move. Basically, it's more important from that. And the way it works is that you have an initial beliefs, and every time that you observe data, you try to move towards the truth. The idea is that you never reach it, because we said before. We said when we defined the idea of probability in the Bayes world. So you will never reach enough comparable situation to have a real observation of what the probability of the truth is. So you will never reach the truth, but you can approach it by increasing the number of observations and updating, and you will be closer and closer to the truth in this perspective. Okay. And we saw it with the binomial distribution. For the exemplification is better because it's easier to calculate, but of course you can fit whatever distribution family you want in the Bayesian framework. So you can do it, for example, with normal distribution, as in this case. And the idea is that you can estimate your maximum likelihood that in the case of using a uniform prior, so without putting any information in your prior, is not influential. But as soon as you plug a prior, so I believe that it should work in this way, now it starts to impact your estimation. And I don't think we need to enter these details, but the point is that it can be used to narrow your estimation if you have good evidence, if you have good reason to believe in something in advance before running the experiment. It could help to shape somehow your expectations, and this could be a potential also a drawback of the techniques, because if you put too much information in your priors, then there's no data that can convince you to change your idea. So the prior point is the complicated things of the Bayesian statistics. That's the point. So you have a narrower estimation after the blue line is within the same data. Non-Bayesian estimates is your maximum likelihood estimation, and you have this kind of distribution, and you have this picking parameter here around. It's wider, and you have this, after the Bayesian estimation, you have this narrower situation. It's better. I don't know. I don't have, honestly, a clear answer, because it's better if it's closer to the truth. But if you start with the wrong prior and you didn't collect enough data to really shape your your posterior beliefs, then you are still with your prior beliefs. So basically, it's meaningless to collect few data in this situation. Okay, you just stay with your prior.
So
Yeah.
would you say that you could say to people, okay, this evidence is useful for people who have this prior, and if you have that prior, the evidence is not useful.
We will go to that. The point is that because you have to declare the prior, it's transparent how much you are shaping your data, basically, with your prior. So there's subjectivity, and maybe another researcher would say, I don't believe in that prior, this is too strong, and so the results are not convincing me.
But rather than try to solve the question of what is the accurate prior,
there are some suggestions, but the point is, again, we go back to the subjectivity. So the subjectivity is part of the Bayesian world, and there are some attempts to deviate from the subjectivity, trying to use more objective prior, let's say, but they are not very convincing yet. So subjectivity is still within the Bayesian world. There are some ways that you can make it more transparent, less informative prior, and the point is that if you have enough data, then you can put the prior that you want, but the data will win, basically. Yeah.
I think there is also one way which Bayesian statisticians try to deal with this, which is the sensitivity above different kinds of assumptions.
Yeah.
So basically you do a sensitivity analysis, you see how much the results that you have are robust on different types of assumption about the prior.
Yes.
So there are situations and that it is
and we will see, because there's an easy way implementing just to this. So it's prior with robustness, or robustness prior, robustness check is called.
But again,
you try different priors. Yeah.
So there's a classic paper in Perspective, Psychological Science 2011. The title is Bayesian Code Smuggling Priors into Rotterdam Harbor. Bayesian Code Smuggling Priors into Rotterdam Harbor. It's about how you manage, ironic failure. Ironic piece is how you can manage to have end results by changing the priors without being caught that you are modifying the priors as a way to achieve the results. I mean, this is the reason why, sorry if I forget, this is the reason why Fisher was adamant against Bayesian, because he saw the risk of starting from the end, justifying the priors as a way to, to say my conclusions are correct. So you can work the other way around. You can fix your posterior. You can find a prior that is in line with your posterior. The point is that it can be caught. The point is that you can see that this is done because the priors is aligned. But that's exactly the discussion that Fisher had for years against Bayesian because of the subjectivity aspect.
Yeah. Again, subjectivity can be really took out of Bayesian statistics because it's in their definition, but you can control for it, and you can check for the reliability of the researcher and how they behave, basically. In my vision, it's transparent way, but you cannot really exclude subjectivity from the Bayesian statistics. Okay, so we are at the prior. Data are the data, but what is the prior? Okay, this is once again the bias theorem. Now we put the attention on the prior beliefs, how we can decide prior beliefs. So we know that bias factor, which is the most commonly used outcome of Bayesian statistics, is very sensitive to different priors. The posterior estimation are a little less, I have to say, so they are still sensitive if you have few data, but less for several reasons, but still they are sensitive to different priors. So understanding which prior should be plugged in your analysis is important. Now, there are some standards, and now the fact that it's more and more used is going also in facilitating the definition of some standards that works. Okay, but every good Bayesian, so not me, but every good Bayesian suggests to have personalized priors in your analysis, to specify why you are using their priors, but use your priors. Okay. But there are also some standards. So for example, a normal distribution with mean 0 and standard deviation of a sigma of 10 gives you balanced results between a good parameter estimation and a reliable bias factor. If you want to put more emphasis on the parameter estimation, the suggestion is to use students T with mean 0 and standard deviation 10 with 3 degrees of freedom. Now you see how arbitrary can look these priors. They work. If you plug in your analysis and you have enough data, they show that they work. There's no real good reasons why they work. Another very common prior for the analysis is the Cauchy with a mean 0 and an R scale of 0.707, which is a square of 2 by 2. This is very common because it works very well in having a safe and good bias factor estimation. So because it's the most common output bias factor, most people use this one. More personalized priors that still follow standard rules have been suggested in 2019, and these others suggested to use normal distribution with standard deviation coincident to the clinically relevant difference divided by 2. So I put my normal distribution on the center that I need. Usually it's a 0. And I divided my clinical relevant effect, or the same thing but with a Cauchy divided by 7 for the scale factor. Again, they work. There are no particular reasons why they plug these numbers, and they work. Another nice, interesting procedure is to use elicited priors. There are different ways to elicit priors. You can have really naive priors, so ask people on the street, oh, what do you believe about this? And they give you priors. Or you can ask experts. So, for example, you can run what once was a pilot study to have a good balance in your trial could be run for having elicited priors. Okay, so you can have these procedures. Now there are also web-based applications to extend to your community this kind of situation. So you can have real priors. So they are real beliefs of expert people that can guess. They do their best to guess this. This paper was interesting also because it was quite recently shown in 2021 that, yeah, it affects your conclusions, the priors, but if you do your job well, rarely changes the qualitative conclusion of your decision. And we will see, I didn't put the slide, or maybe I put the slide later, but the point, no, I put the slide later, sorry. The point is that you have to pay attention to your priors. You cannot just put whatever number. But if you don't know what to put, just use one standard and collect more data. Okay. If you have good reason to have good priors, solid priors, then maybe you don't need that much data, and you can trust on your literature, for example, or your previous 3 experiments that you already collected, and you can trust to plug additional information in your experiment. But what is important and risk is that we should be aware of what does it mean to put prior. First, we are not always aware of what we believe. Okay, so for some things where we are expert, that's fine. We can have a good and reasonable belief about that. But in other situations, maybe not. So, or if we ask to experts, or we use standards, or if we really plug our opinions, yeah, it works. Bayesian statistics works on that, but maybe it doesn't worth the effort. The other important point is that it can be complicated to transform beliefs in distribution. So if we speak about stuff like what we discussed up to now, it's more easy. But it can be not such an easy translation to pass from your beliefs to a distribution, because you have to put numbers on that in the end. And another point is that it could be difficult to be surprised by your data. If you put too much information in your prior, you will stick with your prior. So finding a balance between how much trust put in your prior beliefs and how much trust in the data, it can be difficult. And another point is that if you don't allocate probability in some solution, there's no data that will make you believe in that. So I put this picture of the flat Earth because a good scientist don't believe on flat Earth, but would never put the probability of 0 on it. Maybe it's 0.000 thousands of zeros, but then a 1 comes up because you need that data could make you believe in that. Another example that usually I remember a lesson by Wagemakers is used about extra aliens life. Okay, from they used to say, yeah, we need more evidence, but we need to keep the possibility that the evidence will change my mind. Okay, if I put 0 on that probability in a prior, I will never trust on it, because you actually multiplicate things, the prior by your evidence. So anything by 0 is 0. That's the point. Okay, and another point is that you may be trapped in keep believing in things that repeats as inevitable, because you continue to narrow your belief, narrow every time that you update your beliefs, and you may become more insensitive as much to rare events, for example. Yeah, for example, the case of the disease. If you stay with one test, you still believe that you have 9% chances of being sick. So if you have even stronger beliefs, prior beliefs, maybe you need 100 tests before believing that you have the COVID, for example. So it's complicated. Okay, I think it's a good time to play a little bit with numbers, so to see these things still theoretical with numbers. I don't know if you had time to download JASP. They added this very good button that you can find under this plus symbol that it's called Learn Bias. And this is a tool just to play with the numbers and in the Bayesian world to understand the mechanics. So, for example, it works only with the binomial and beta, so it's just simple part. But you can also play now. I'll show you some data, but you can also play by yourself to understand better how your changes influences your results. So let's say I did my homework and I prepared this very complex string of results. You see, 14 data, sorry. And we have 9 success and 5 failures. This is the sequence, and we have this proportion, okay? So it's more or less 0.65 against more or less 0.35. And we can try to see how different priors, if you don't, there are questions, sorry?
So I open JASP and they say, so open the data frame.
No, you don't need to open the data, you have to go, sorry, here under this plus button, and you can add a module that is called Learn Bias. And now there should be on your main menu. Okay. And you can press on it, and it should open a menu where you have different options. So now I show you a few of the results, but it's very intuitive for trying different stuff. For example, you can insert in the data directly the odds, your results, so 9 and 5, for example. I put the sequences because if you put the sequences, you can run another control analysis, which is called the sequential analysis. So it's better if you have the entire string, but otherwise you can only put 9 and 5 and you are already at the same point of me.
Is it testing or Bayesian estimation?
Bayesian estimation by now, testing is for the next class. Bayesian estimation, yeah, maybe I can show you
seconds.
Here.
And the sequence.
Yeah, I show you on the software. Okay, it's here. Learn bias estimation. So it's very small, but you have here under the data menu, you can just put the success, for example, 9 and 5. Okay, so it generates your data. Otherwise, you can, where is it? Enter a sequence, plug the sequence here, you write, and you, so 1, 0, 0, 1, 0, 1, 0, and so on and so forth. You can put the numbers that you want, and then you plug 1 is success, 0 is failure, and it calculates your stuff.
Yeah, this is for sequence, isn't it?
This is for the sequence, but I think it's okay if you just
Because
specify the counts and you put the numbers of success and failure here. That's enough, I think. So then you have to specify your model, so you can press on the plus button and you can press as many times as you want, and for every time that you press the plus, it generates a new model. You can give the model the name that you want, and you can specify the type of distribution. I suggest to keep only one spike and then put the beta on all the others and try different values for all the different betas. And what's the difference? The spike distribution is not a distribution, it's just putting 100% of your density over that value of the parameter. So it's everything is just 0.5 with the spike. While with the beta you can put all the numbers that you want. For example, you can put 10 and 10, or
These are the priors, right?
yes, 4 and 15, so number and 150, let's say, like something like this. So, and you see, as soon as you enter the numbers, this populates this table, and it makes a lot of calculation that we can see maybe better here. So we go back to the slides, but you can play with all the numbers, and it's fine. So I prepared in advance this different prior distribution. You see in the table you have one column with the model, which is the name of the model, one with the prior, which specify your prior beliefs. And I put one spike at 0.5, which is this arrow. There is one non-informative prior. Why it's non-informative? Because it's a uniform prior, and it's this constant line that spreads over all the area of possibilities. Okay, so it's from 0 to 1, and it gives the same density, the same probability to be true to all the parameters. So it's basically it's like not having it, but giving the possibility to react to every proportion of numbers.
So can you again say what the parameters are?
Yeah. These two parameters of the beta distribution is simply the number of failures and success in a binomial test. So it's like an accuracy of a test. So I say yes, no, it's positive, negative, something like that. So you have 1, 1, it means that you put one success and one failure.
Okay.
If you have a 3, 3, is 3 success and 3 failure, which means that you are, again, symmetric, so it's balanced on a theta of 0.5, but you already have some beliefs in that, because you are putting information. If you put 100 and 100, you can try, you will see that it shrinks around the 0.5. Okay, So I put this distribution. The beta is non-informative. The symmetric is 3,3. You see this gray line here. Then I put a weak asymmetric, is this one, 5,3. You see that rises and has space to go down. And then I put a strong asymmetric distribution, which is the green one that goes this way. Okay. And this gives you the prior mean. It's the mean of your prior distribution, simply the proportion of your prior parameters. Now we update our beliefs with the data, the 9-5 success failure that we entered before. I show you how to plot this graph, although it's very intuitive in JASP. And we see what changed. Now we have all these lines that moved basically towards the point of our proportion, because, I mean, data matters a lot. Okay, so everything is moving toward the point of our estimation, but still we see that they are not overlapping one with each other, because the prior also matters. And one key observation that we need to do here is that the spike doesn't move. The spike stands there, because, again, we are not allowing to move to this distribution, because we put 100% of our prior distribution over that exact parameter. So there's no data that will change your mind. And how to, okay, we can see the separate lines. So the x dot is the proportion of our observation, and we can see the prior is in the dashed line, and the solid line is the posterior. So you see the one with the highest discrepancy between the prior, the posterior, and the actual observation is the strong asymmetric distribution, because we have this big ramp that shifts towards the proper proportion, which was just above 0.6, but couldn't reach, stand in 0.75. So if I'm plugging this prior in my research, I'm putting a lot of information, a lot of beliefs in the fact that it was really asymmetric, my coin. That was really unfair.
The idea is to stay closer to the prior.
The idea is that if your posterior is close to your prior, it means that your guess was correct. So you had a good guess. Now, this trick, you can use it in testing hypotheses, because, for example, we will see it, but the idea, for example, for the t-test is that you calculate a delta. So the f-tech is calculated as a delta. You put the prior on the 0, and you see how much your delta shift your prior that was 0, to understand if 0, so for example, the absence of difference was close to your data or not. So you can use the prior also to test hypotheses, even if you don't believe in the prior, for example. But we will see a bit better later. But yeah, the idea is that if your posterior is close to your prior, it means that your initial guess was correct. Or to say better, that the data are reinforcing your initial beliefs.
Could I just go back to the learn base in JASP? So you entered the data. You said
yeah, it's here. So we entered the data, and actually it already updated, because this is very small now. Sorry, where is my mouse?
Yeah, I can see.
Preferences.
So the posterior takes into account the data.
Yes.
Yes, exactly.
Counts.
Okay, so you already have a posterior calculated in this table. If you want to see it, you can have, where is it? Inference, standard inference, you can have all the plots. So you can, for example, having the prior and posterior plots. And I want to plug also the observed proportion. So this is calculated, I put these 4 models. So this is the spike, this is non-informative, This was my symmetric inside here, and I put this strong, very strong asymmetric prior with a 14115, and you see that my data were here, but I put so much information in my prior that basically didn't change my mind.
How do you show the graph?
Yeah, I show under inferences, you can just tick this one to show the prior and posterior overlapped, or one the overlay over the other is prior and posterior distribution, and it creates one graph for each of the different models. But you can also have only the posterior, and you can. This is only the posterior.
This is for sequential again? Or?
No, the inference is using just the count data. For the sequential, you need to enter the sequence, and you have a new menu here that now I can't click on it because I didn't put sequential. So I cannot click on it, but you can click on it, and you have new graph that you can plot. And the posterior prediction, we won't enter this one, because it becomes more complicated, but basically it uses your prior information to estimate your next 10 subjects, for example, or 10 trials. So you can use this information to have an estimation on how they will behave, considering your actual observation.
So if you look at it from this way, you cannot only have a belief about what an effect is, but also you can have certainty in your belief.
Yeah.
Because the more numbers you put in your data,
Yes.
the more certain.
Exactly. The point is that if you put too much emphasis on your prior, then your data are little influential on your posterior, which means that they hardly change your mind. So basically, you are running an experiment just to say yourself, "Oh, I'm good," but you're not really looking at.
Why a prior and a posterior are not a probability. They're a belief.
I believe exactly. I believe.
Certainty.
A probability under the subjective probability consideration. Yes, you're correct. Indeed, pure Bayesian call them beliefs. Again, it could be useful. It could be also tricky and sometimes misleading if you put too much emphasis on that. Now, if you use the priors that I told you before, both the personalized or the standard, you won't be in the situation that data doesn't work. They work. With that priors, data are more influential than your priors. The prior just help you to shape a bit your distributions. So they are not very influential. And I didn't read because it was too much, but there are also methods that have been developed to, I mean, I didn't want to enter this point, but another difference is that Bayesian statistics assumes that you have all the information that you can have at this stage, and what is variable is not the data, but it's the parameter. So the point is that this can get complicated when you speak about sample size, for example. How much participants we need to have a reliable estimation. This is not a real question for a Bayesian perspective, because it assumes that you already collected all the data that you can. And you are trying your best guess with the data that you have. If it's 5 participants, your best guess is with 5 participants. But this means that your prior count more in that situation. If you have 1,000 participants, it's hardly influenced by your priors unless you have a super strong prior. So again, it's a different perspective, and not everyone should use it.
But I think I found the Bayesian framework more intuitive than the Milano-Bicocca distribution. Because you essentially, for example, when you see a paper and you see that you report the result and it's p equal 0.05, and when you do interpret the result, I think we still act as Bayesian intuitively. For example, you find the outcome, yeah, but I don't believe that, because I wouldn't believe that people,
Yes.
I don't know, the stroop effect doesn't work with a blonde male person. So that's, I mean, something I wouldn't believe so easily. So I think P05 and a small effect size don't convince me at all. That's Bayesian. So yeah, I kind of like it.
I beg to differ. I'm not entirely. I mean, there are merits, Bayesian, so nothing. But we just said that's Bayesian. There is a recent paper by Lakens that says the best alternative to the p-value is a correctly used p-value. What I mean is that there are assumptions. So if you violate this assumption, you can say you are thinking Bayesian, but simply you are violating assumptions that are behind the p-value. So I think there is would require a kind of long discussion, but for instance, one problem here that you are hinted at, what does it mean that you have all the information? It means that you don't have the concept of population. It means that if your data is skewed, you're gone. That's bias. For sure you're going to make the wrong decision. There is a paper by Baden-Marcus in 2007, Journal Mathematical Psychology, in which she makes the claim that less data are better than more data. If you achieve significant value with less data, it's better than more data. Because if you work bottom up and you think the data are perfect, of course it's about consistency. It's not about the value. So it's okay, it's great, but really can get you wrong. On the other side, you have a population assumption, which means that you always say, I don't know, I have no idea. But suppose that that's correct, this is what you do. So I think that if you do it correctly, that keeps you in check, as it were. But again, I'm not against Bayesian. I really think it's great. I just think that one has to be careful. There are different kinds of pros and cons in both.
Yeah, I try to stress this point because
Sure,
we should pay attention to all the assumptions. I think that another plus of Bayesian is that it makes more clear also the need of the assumption of the null hypothesis statistical testing, because it pushes somehow, let's say, the other side of inferential statistics to be more clear on the assumption, on the meaning of the p-value, on the how much you should check all the assumptions that you made, or how to interpret p-values and confidence interval, for example, which is in the Bayesian world is straightforward. It's the probability to find your parameter over there. In the frequentist approach, it is not directly the probability of having there the true parameter, your parameter. But yeah, I think another plus of Bayesian, connected to what you were saying, is that they somehow try to model uncertainty. So they are not saying that this is the parameter with a sort of error, but that the parameter is somewhere over all the space with certain probability to being there, but it's still over the entire space of the possibility. So try to model the uncertainty and to make it more declarative, let's say. But again, I agree with you, and that's also why I approach Bayesian stuff, because it's nice to have this discussion. I think it's positive to have this discussion because it's about how we trust our experiment, our data, how we finally decide this is correct, this is less. I cannot put all my trust on this paper because they violated this assumption, and so on and so forth. So I think it's useful overall, even if one doesn't want to use this approach, and I find perfectly fine not using Bayesian approach, although I know people that are so Bayesian that think that non-Bayesian statistics are meaningless. I'm not one of them. But yeah, final part of this first part, sequential analysis, which is another good point. Again, sample size is a different way. It is used differently in the Bayesian statistics. One, I think, good way to use sample size is using the sequential analysis, which means look at the bias factor, or in this case, these are the 95% credibility interval, so the distribution of your theta parameter in the 95% credibility interval, after each data entry. So the idea is updating with the Bayes theorem. So every time that you collect one evidence, one piece of information, you can plug into your analysis and rerun and see how it changed. So this example shows that we don't probably have enough evidence to conclude anything, okay? Because every time that I enter a new piece of information, yeah, it moves, but it stays more or less always around my 0.5. So if I would say it's fair or not my coin, probably I won't take a strong decision in this case. But if I increase my number of observation, and in this case is a clear advantage because you don't have to correct or to rerun from zero your experiments. Of course, you can do sequential analysis also with null hypothesis statistical testing, but you have to plan, you have to control for multiple comparison, you have to pay more attention on that. In this case, you are uncertain, you collect more information. You add subjects. And you can do it, also you can do it in a nice way, planning which kind of evidence you need to reach to stop your data collection. But let's say I kept exactly the same proportion. Basically, I just copy and paste the sequence that I showed you, so it's also the same sequence. So, and same priors. You see now the posterior are basically one overlapping to each other. So when I have a lot of data, the posterior is much less influenced by my different priors, unless you put some probability over your space, because the spike stands at 0.5. And this is the sequential analysis. So we were around here before and we couldn't take decisions. Now I increased my number of observation and my credibility interval shrunk, and now maybe I have some stability. I can see that doesn't change that much now the direction of my credible interval and of my best estimation. So, well, it's 200 participants, so maybe I would take the same decision with frequentist approach. But this is a good way to do it, and maybe it could be an efficient way to design experiments. For example, with patients, we can use this kind of analysis if you plan it nicely. There's a method that it's called bias factor design analysis. You can have a sort of standard way of designing this efficient way of collecting data. So you plan how much evidence you want before stopping collecting data. And so, for example, in this case, probably we would have stopped at 75, more or less, or 100, to be very sure. Okay? So, first part, it's over. This was the theoretical part. And in the next hour, now break, I think, and in the next hour, we will see t-test. Yeah, questions, of course.
First, for other cases than binomial distribution, we use means, or for instance, in continuous variables as the prior estimation. What is the unit of work?
For the prior,
yeah.
For the prior, well, you can plug all the distribution that you want, and the standard priors was using normal distribution, Cauchy distribution, and test and student T distribution, which are for continuous variables.
Yeah, but in this case we use counts as a...
Yeah, because it's easier to count. It's easier to plug the numbers and you can solve analytically. When you cannot solve analytically, we will see in the next part, but basically you have algorithm to approximate the posterior distribution, and because you set your prior, and you
prior is
an approximate. It's a distribution.
It's just a distribution.
Okay. Yeah.
Okay.
With a mean, yes, there's a mean. Actually, the Cauchy doesn't mean, but it's a specific.
And second thing, to avoid the standard standard distributions, can you do the split kind of split sample, I don't know, 30% to establish a prior? And
you don't need, because the sequential analysis basically tells you that every time you are already doing it from the participant number 2, basically.
Oh, so
it's like because you put all the numbers together, you don't see it, but you can put one. You can put one participant at a time, and you end up in the end with the same result. So it's not useful to say the first part of my group is my prior. It's different if you, for example, in one study, I had one experiment that was inconclusive, and we said it's inconclusive evidence, but we collected the second independent experiment with different manipulation, and it was connected from one part to the previous study, of course, the previous experiment, and we used the distribution of the experiment 1 as a prior of experiment 2 to see if the new data change the prior that was in experiment 1. So you can use different experiments to prior your next experiments, and it's a good way to do it. Of course, you have, again, to transparently report why you are using such a specific prior.
And the last question, so if we enter distributions in other type of cases, that means in when we test for alternative competing hypotheses, that they should have different distributions, because if they have the same distribution but a different mean, or I don't know, it would be
yeah. We'll see, but the point is that, for example, the most most basic example is the t-test, of course. And in this case, you have the alternative. The null hypothesis is that the difference is 0, and you have the alternative, or that the null hypothesis can be it's greater than. Okay. In this case, you have two competing hypothesis. One is the difference is 0, and the other one is the difference is not 0. You can put your prior on the 0 with a certain scale factor. So you allow to be not exactly 0, even if you put your prior just on the 0, and you give probability to its neighbor, basically. And you see how your evidence shifts from that value. So if you have strong evidence that the real parameter is 0.75, then your distributions will be shifted on the right, and you have a big discrepancy at the 0 point, and this is used to calculate, for example, the Bayes factor, which is how much the evidence change your odds from the prior to the posterior. So how much the data change your mind. You can have also multiple models. For example, we will see briefly with the ANOVA, which is not exactly the ANOVA. It's ANOVA because it's easier to understand for all the people. It's called Bayesian ANOVA, but it's model selection. Basically, you have one with the main factor, one with the main factor and the interaction, and you test which one is better predicted, better fit with the data. That's what we are going to see in the next time. Yeah.
Maybe this was discussed already, but in the output, like, it gives me a posterior beta, and like if I introduce it again and again, I get with the posterior mean closer to 1, and like this is the objective, to get the best posterior mean to be the closest to 1, like when I.
Or maybe didn't get. So I can check your output.
Like, do I have to get this as close as possible to 1?
No. Okay, on the output, you have to make sure to everyone. So you were asking if this one to be good should be close to 1, right?
Right.
No, this is a proportion, okay, that includes already integrated the prior and the posterior. Now with the beta, it's nice, it's easy because we know that we collected, now I don't remember, but it's like 14 evidence, yeah, 9, 5, 14. So I know that the new data are 14 and the prior is 1 and 1. So now I have 10 and 6. So you see it's just the sum of the new information with the prior information, because it works in this way. The multiplication with the beta and Bernoulli distribution is just the sum of their of the information that they have. Okay, so it's one, let's say head and tail. Okay, and I collected 9 head and 5 tail. I add this 9 to my 1, and that's what you do with the sequential. So imagine that it was 8. Okay, you see now it's 9, 6. I had another success. Now it's 9, and it becomes 10 and 6. Okay, that's what it does after each new piece of information. But this is just with the beta and the Bernoulli, which is easy. Now, when you go to other distributions, it gets complicated, the calculation. But this is just the posterior mean. So it's the peak of your posterior. So this one is 0.16 because it's here. So this is good if it's, well, no, this is your best guess considering both your prior beliefs and the new evidence of information. That's your best guess. Okay? I killed you. Okay, Frank.
Thank you.
Could you then say that, so you have this distribution of possible, basically we would say that's the distribution of theta values, so actual probabilities that you could live with.
Exactly.
And then the mean of that distribution is the content of your belief. You say, okay, this is the probability that
that's what you usually you always report the credible interval, because